This lesson is about the electrical system. This is extremely important. The electrical system impacts every other section of the house. House fires are caused by electrical problems. The main panel is a fire prevention device. Make sure you pay attention to all the elements and all parts of this lesson, because everything that we do is about the safety of the family living in the home. So let's get started.
Now I'm going to show you how to perform an inspection on a main electrical panel. So one of the things that we want to do before we actually touch the panel is we want to make sure we're in a safe location. There needs to be a 3x3 invisible space, so nothing is disturbing that space. If there's any water on the floor, that doesn't mean that you need to perform the inspection. When it comes to electricity, the number one item is your safety. All right? As you can see, everything is going to be dry here. So we're going to make sure that there are 6 screws on the panel. We're going to open up the panel. And there's a few things that we're just going to generally look at. One, we want to see if there is an inspection sticker on the panel. And I'm not seeing anything right now, so that's definitely a defect. All right, and that inspection sticker is by a third party. So when you have a licensed electrician that installed the panel, a third party is going to go and ensure that it was done to the NEC code. All right, so while we're looking over here, we can see that items are properly labeled. We don't have any missing or any open slots. And then we can see that we have a 150 amp breaker. Now, one of the things that we always do is we're going to open up this main electrical panel because we want to check the wire sizes relative to the breaker. So let's get to that. All right, so here we are. So let's pull out your checklist. Today I'm actually using my phone for the checklist. And one of the things that we're going to identify first is the main electrical panel is located in the basement. So we're going to check that. Location of a distribution box. I haven't seen a sub-panel distribution box, so we're going to check no at this point. All right, location of the main disconnect. The location of the main disconnect. Now, to let you know, I never stick my hand in any type of box. I always end up using a voltage tool, just more or less as a pointer. So here, our main electrical breaker is 150, and it's by itself. On some systems, it could be among the breakers on the older systems. So we're going to mark that down. The type of protection. Typically, we have circuit breakers. You can see fuses. We don't have any here. So this is where we're going to begin looking at each individual breaker and see if the corresponding wire is appropriate for the size. So here we have a 20 amp breaker. Now, it may be difficult to actually say to yourself, so what size is that? If you don't have any reference wires, maybe you get at Home Depot or Lowe's, what you would end up doing is look at a wire and then you're going to look at the sheathing itself. So if we look over here, and sometimes you got to pull out your flashlight to look along the side, and this is one way to do it. Is it a little bit more difficult? Yep. All right, so that is 12 gauge. So we have a 12 gauge wire here. We got the proper size for the 40. Here again we have another 12. We got a 20 amp with 12, 20 amp with a 12. We have a 20 amp with a 12. Oh, here we have a 14 gauge wire with a 15 amp breaker, so that's definitely appropriate. So we have a 15 amp with a 14. And we have 12 again. We have 12 again. We have 12 again. On our 30, we have a 10. All right, so by individually making sure that the wire sizes are correct with the breaker, that means the possibility over any overheating of the wires is not possible. Now, one of the things that you have to make sure is that an electrical panel is not a distribution box for power. This panel and all panels are safety devices. All right, so no fires are occurring. So if there's any overheating of the wires, these breakers will actually pop and stop the energy being pulled to that particular location through the branch circuit. So we got to remember that. Not for distribution of power, but are considered a safety device. So as we go back to our check sheet, we're going to identify for each of the breakers what were the wire sizes. So 15 amp was 14, 20 amp was a 12, 30 amp was a 10 gauge. Now once we do that, we're going to begin to look at the grounding. We want to follow this ground wire. So let's do that now. So where is, yep, right there's the ground wire. Let's put this in here for now. So there's our ground wire, and we can see it up here, right there. And now we're going to try to follow this through. Oh, here's our ground wire, so we're going to continue following the ground wire. And now it's going to come down to this is actually on the street side, so we actually have a water meter. So we have the grounding on the street side, and this is a defect. What you want is what is a jumper wire, a ground wire connected to this connection, and then on the other side of this meter, what this meter does is actually act like a light switch. It creates an open circuit. So we want to wire from this location onto this. So this is definitely a defect. So what we're going to do is go into our system that we have right here. And there's many ways. You can do this on your sheet, and or you can actually, what I do is I tap it, I hit the microphone. Noted, at the time of the inspection, a missing jumper wire over the water meter, period. Recommend to contact a qualified contractor to repair as necessary, period. I'll hit repair, and there we go. Now the next item is we want to make sure that the connections are secure, which we have. We have a main water, if the ground is to the main water, and we talked about the missing jumper, but we also want to see if there's a ground rod. When we were doing the exterior ground section, or excuse me, the exterior wall section, I didn't see a ground rod. That doesn't mean it doesn't exist. It could be buried, but it's not visible. So I would definitely point that out. All right. And then the last item we have here, aluminum branch wiring. So let's take a look back at the electrical panel here. And we're going to look for aluminum branch wiring. Now, you're allowed to have stranded aluminum, which you have right here. And that's completely acceptable. What we don't want is a single strand aluminum. Because this is all Romex and there is no cloth wiring, all right, I didn't see any aluminum wiring. So today we do not have any single strand aluminum wiring. So when it comes to an electrical panel, this is a critical item for performing a home inspection. One, we want to make sure we're in a safe condition to perform this this electrical inspection. But two, we want to make sure that we have the proper wire sizes with the appropriate breakers. We want to understand what is the main breaker size, just in case if it is smaller, for example, a 60 amp breaker, in today's condition, that is pretty much a limited electrical main panel, and we're going to probably request a upgrade to at least to 150 or to a 200 amp breaker. So this is how you perform a electrical inspection on a main electrical panel.
This lesson is primarily designed to help you understand electricity and how it works throughout the house. This lesson has been written to try and take the mystique out of what most people are somewhat afraid of: electricity. Electricity, if handled properly, is safe. Electricity, handled improperly, can kill. As a home inspector, you will have to visually inspect the electrical components of both exterior and interior of the house, including but not limited to, attachments and/or structures, as well as the property and surrounds of the house. There are 3 areas that we need to be concerned about with the electrical system. Exterior, where the meter is located. Interior, at the outlets. And 3, the electrical panel, where the branch wiring and circuit breakers or fuses are located. These areas are all covered by different checklists on the worksheets. It is important for you to know what you are looking for and why it is important. Your clients' lives may depend on how thorough you perform this part of the inspection. Home inspectors shall observe and report upon readily accessible and observable portions of the service drop, service entrance conductors, cables, and raceways, the main and branch circuit conductors for proper overcurrent protection and condition by visual observation after removal of the readily accessible main and sub-electrical panel covers. Service grounding. Interior components of service panel and sub-panels. A representative number of installed lighting fixtures, switches, and receptacles. A representative number of ground fault circuit interrupters. Home inspectors shall describe readily accessible and observable portions of amperage and voltage rating of the service, the location of main disconnects and subpanels, the presence of aluminum branch circuit wiring, the presence or absence of smoke detectors and carbon monoxide detectors, the general condition and type of visible branch circuit conductors that may constitute a hazard to the occupant or the residential building by reason of improper use or installation of electrical components. Home inspectors are not required to observe and report on remote control devices, observe and report on alarm systems and components, observe and report on low voltage wiring systems and components such as doorbells and intercoms, observe and report on ancillary wiring systems and components which are not part of the primary electrical power distribution system. Insert any tool, probe, or testing device into the main or subpanels. Activate electrical systems or branch circuits which are not energized. Operate overload protection devices. Observe and report on low voltage relays, smoke and/or heat detectors, antennas, electrical de-icing tapes, lawn sprinkler wiring, swimming pool wiring, or any system controlled by timers. Move any object, furniture, or appliance to gain access to any electrical component. Test every switch, receptacle, and fixture. Remove switch and outlet cover plates. Observe and report on electrical equipment not readily accessible. Dismantle any electrical device or control. Measure amperage, voltage, or impedance. Observe and report on any solar-powered electrical component or any standby emergency generators or components. Service components carry electricity directly from the transformer on the pole to the main electrical panel in the house. The service components are defined by the 3 different electrical wires. Service lateral, the triplex cable, the service drop, and the service entrance. The service lateral refers to the electrical wires running from the utility pole to the home. Electrical service is provided by the utility company at the city street. Generally, the service lateral is carried along the street on aerial or underground cables. If the service lateral is carried along overhead cables, the service lateral to the house is a triplex cable. Usually, two 120-volt black or hot wires and a third white or neutral wire that is insulated and usually twisted around a metal cable, which is sometimes used as the main ground. Typically, 200 to 240 volts of alternating current, or AC, is supplied to residential dwellings on two separate lines of 110 volts each. The AC can change from 0 to over 110 volts and then to less than 110 volts and back on a 60-second cycle. With that, the service is described as 110-volt alternating current at 60 Hz. Typical distance from ground or structures for the service lateral. If the service to the house is underground, the service to the meter is still called the service lateral, although the service lateral is contained within a plastic conduit which terminates at the meter. The cabling is not visible in this situation. You will just be inspecting the meter and the meter housing. Service drop, above ground service. The service drop is the wire running from the weatherhead to the electric meter. This wire must be securely and safely attached to the house as it runs to the meter. It should be checked for deterioration and fraying. The insulation sometimes becomes so worn that the bare cables are exposed. The service drop should be properly sealed at the entrance to the meter to prevent water infiltration. Sometimes the service drop is housed in a metal conduit and is not visible. Service entrance. The service entrance is the wire from the meter to the main panel's supply side. Sometimes this wire is not visible because the main panel is on the other side of the meter and no wire is visible at the point of entry. Once in the panel, the two main supply lines are connected to lugs which are attached to two separate bars, commonly known as bus bars, carrying power to the breakers or fuses. The overhead service supply will be attached to the house in many ways. Usually, the wires are attached to a mast. Older homes will have a wooden or steel angle mast running down through the roof of the home. When checking this type of service, be sure to check the point of attachment. If this is loose, it could cause some problems. The weatherhead is where the service wires enter into the conduit. Make sure that this area is in good repair. The wires should droop downward just before they enter the weatherhead. This is called the drip loop. The drip loop simply allows the water to fall off rather than entering through the weatherhead and down the conduit into the house. Here are the checklist items to inspect that you saw in the exterior walls lesson. You will inspect these elements of the electrical system when you are outside inspecting the walls. Some common defects that may be observed when inspecting the exterior electrical system are threatened wires, wire clearance from roof lines or window openings, or limbs of trees. Improper drip loop, the service drop not safely and securely attached. Service drop insulation wrap is deteriorated. Electrical meter seal at top is not properly caulked or sealed. Service entrance through the wall or siding is not properly caulked or sealed from the weather. The service entrance wire terminates at the main panel. The purpose of the main panel is to protect the branch circuits from an overload. It may look like a distribution point, but in reality, it is a fire prevention device. The house is broken down into multiple circuits or branches. Some of the branches handle electrical equipment like dryers and stoves that need a large amount of current. Those circuits require wires that are rated large enough to handle the higher loads. For example, 8 or 10 gauge wire. Other circuits are only connected to outlets, switches, or lights, and they only require a 12 or 14 gauge wire. Wires that are forced to handle more current than they are designed for overheat due to the resistance. Imagine a filament in a light bulb. It is extremely important that the correct load, wire, and breaker are all matched properly so that the wires don't overload, heat up, and start a fire. Most residential fires are electrical in nature. One point needs to be emphasized. A wire will only carry the current that is specified by the load. If you turn on a light bulb that draws 1 amp, and it is the only load in the whole house, then the most that would be on any cable throughout the house is the 1 amp. The amount of current on a wire depends on how much current is being drawn. We see the wrong size breakers on the wrong gauge wires all the time. There may never have been the current going through that would overheat the wires, but that does not mean that the wires are safe. Always check your wire size and your breaker size. To determine the service size, you must determine which component has the lowest rating: the service drop, service entrance, or main breaker. For example, if the service drop is a 200 amp rated wire, the service entrance is a 150 amp rated wire, and the main breaker is a 100 amp breaker, then the service size of this house would be 100 amps. If the house had a main breaker of 200 amps in this example, then the service size would be 150 amps. This would be reported as a defect, because the 150 amp service entrance cable would be overloaded before it tripped the main breaker, which is too big to protect the smaller cables. The breaker is the defect, not the wire. Remember, the breaker should equal or be smaller than the lower of the two components, the service drop or service entrance. Standard practices today recommend 2 sources of ground. Typically, we find a ground wire clamped to the city water entrance. A common second source would be a ground rod. Sometimes, there may be 2 ground rods when the water is supplied from a private well. These 2 ground rods must be located further than 6 feet apart. The branch circuit breakers protect the branch wiring going to the different devices in the rooms of the house. These are generally 14, 12, or 10 gauge wires. A 14 gauge wire can safely carry a 15 amp load. A 12 gauge wire can handle a 20 amp load. The home inspector, when performing an electrical inspection of the main panel, must take off the cover and match the proper size breakers with the wire that is handling the current. A 14 gauge wire protected by a 20 amp breaker is a safety defect because the wire could overheat before the breaker is tripped. The circuit could have extended periods of 18 amps on it. The 20 amp breaker won't break while the 14 gauge wire is overheating. This will start a fire in the walls and may lead to property damage, injury, or death. This is one of the most important things we inspect. Remember, a 12 gauge wire on a 15 amp breaker is not a safety issue because the wire can handle the current. It may trip the breaker frequently and be a nuisance, but the wire will not be overloaded before the breaker trips. You are really only looking for wires that are too small to be on breakers that are too big to protect them from overheating, like a 12-gauge wire on a 30-amp breaker. To better determine the proper size of a branch wire, go to an electrical supply house and obtain 8-inch samples of 14, 12, 10, and 8-gauge wires. Wrap them all together and put them in your toolbox. When you are at this point of the inspection, compare your sample 14 with any of the wires on a 20-amp breaker or larger. If they look the same, then write up the defect. Do the same every time for all of the breakers, and eventually you will be able to do this without the aid of your sample wires. Distribution box, also known as a subpanel, is an electrical component that expands the circuit breaker capacity. This is the preferred method when expanding a main panel's capacity. Normally, the subpanel is installed next to the main panel, in which one of the slots on the main becomes the main breaker for the subpanel. For example, this breaker may be a 30, 40, 50, or 60 amp breaker. Therefore, the subpanel does not need a main disconnect since the breaker in the main panel is protecting the subpanel. The typical defect noted when inspecting subpanels is the circuit coming to the subpanel is not from its own circuit breaker, but is from a double tap on the main lugs or main breaker. This is a safety hazard. Some of the typical defects are no main disconnect, double tap breaker, aluminum wiring, rust, and knob and tube wiring. A residential house should have a residential panel. All residential panels, designed for the residential market, have a main breaker. If you see a main panel without a main breaker, write this up as a safety defect. There are some home inspectors that say the main panel is safe as long as 7 swipes of your hand will turn off all of the branch circuits. If this was so, why have main breakers? The fact is that panels that don't have a main breaker are designed for and used in commercial applications as distribution boxes. They are not designed for use as a residential main panel. They may be electrically functional, but their use in a home is not appropriate. A double tap is defined as 2 branch circuit wires installed in one circuit breaker. This is a safety hazard and a defect, because the 2 wires will micro-arc and cause the breaker to fail. The early failure of a breaker defeats the purpose of having a breaker protect the circuit. This is a fire hazard. Some breakers are designed for double taps, but that can't be determined without removing the breaker from the box, which is beyond our SOPs. Write up all double taps as a safety hazard unless you can clearly see the double tap icon. Double tapped wiring is okay if the circuit breaker is designed for 2 conductors. If a circuit breaker is designed for 2 conductors, this will be identified on the right side of the breaker, and the terminal of the circuit breaker will be constructed to hold 2 conductors in position. Aluminum wiring was used in residential housing from the mid-1960s to the mid-1970s because of a copper shortage caused by the demand needed to supply the Vietnam War effort. Aluminum is a softer material than copper, which was used for connections and screws in the box and/or in outlets around the house. Aluminum and copper have different thermal expansion properties, therefore expands and contracts at a different rate when current is running through the wires. The connections become loose, causing micro-arcing and the breaker to fail. This is a safety hazard. Aluminum wiring can be safely used if the breaker and the outlet or switches are rated for aluminum wiring use. Breakers are marked for this rating for aluminum, but it is not possible to determine if outlets are so rated. When you see aluminum branch wiring in the panel, write it up as a defect. Finding rust within the main panel or subpanels is a defect. A rusting panel can be caused in two different ways. A very wet basement will change the humidity in the basement, causing all metal items in the basement to begin to form rust. Another way rust forms in the main panel is if rainwater finds a way into the main panel box by following the service line. It may be in the insulation sheathing, or it may be filling the meter up outside and coming along the cable. Either way, rainwater will deteriorate the metal components inside the panel. The rust on the screws and connections will cause microarcing with the wires in the circuits. This will lead to premature breakdown of the breakers, which will lead to breaker failure, which will lead to a house fire. Anytime rust is noted in the panel, it is a safety hazard and should be written up as a safety defect. Missing covers or knockouts. These are areas where things can be inserted into the electrical panel even when the front cover is in place. This is also an intrusion area for mice and other pests that seek the warmth of the electrical panel. Always recommend any open holes be covered with an appropriate cover. Knob and tube is the first system used for residential wiring. This type of wiring was first used in the 1890s and was last used in the 1920s. If you observe and detect live knob and tube wiring in a house, identify this as a safety defect. This is a safety defect since the original wiring was designed to carry less electrical current than today's standard wiring. As the electrical load increases, the old wires get hot and can become a fire hazard. Other concerns with knob and tube are the cloth insulation is susceptible to deterioration, no ground wiring, therefore increases the possibility to an electrical fire and damage to sensitive electronic devices, and improper modification to the knob and tube when using Romex wire. And insurance companies may not insure the house. Fuses are electrically superior to circuit breakers because breakers can fail to trip, while a fuse cannot fail to burn. The problem with fuses is the homeowner will alter or modify the fuse system in order not to lose electrical service or have to go buy more fuses. This can be in the form of a slug or a bigger amperage fuse. Circuit breakers were first used in residential homes in 1935. The advantage of a circuit breaker in residential housing is the circuit breaker can be manually reset and therefore less likely to be tampered with by a homeowner tired of buying and replacing fuses. The inspection of a fused system is the same as an inspection on a breaker system. As a home inspector, you should be aware that many insurance companies will no longer insure a home that is protected by fuses, and you need to caution your client to check with their insurer to be sure that they are eligible. The final section of the electrical system consists of the wires, receptacles, and switches. BX cable was developed for residential wiring purposes in 1899. It was replaced by Romex or NM non-metallic sheathed cable in 1926 because Romex was easier for homeowners to use. The armored-clad sheathing around BX makes it hard for homeowners to install and rewire. There are no issues with BX. The only reason we need to be aware of it is in verifying aluminum wire. Aluminum wire was never used in the era of BX. Anytime you see a silver-typed wire, look to see how it is jacketed. If it is BX, then you know it is not aluminum. It is tin-clad copper. Years ago, wire manufacturers were coating the copper wire with tin to make it more durable. Do not be fooled into reporting tin-clad copper as aluminum wiring. Determine what jacketing it has and call it out accordingly. GFCI, Ground Fault Circuit Interrupter. The GFCI breaker was developed in the 1960s. It provides protection from electrocution when a person is around water and electricity. The electrical circuit is GFCI protected, and thus the breaker will quickly break when the user gets shocked, thus preventing electrocution. GFCI protected circuits should be found in bathrooms, kitchens, laundry areas, unfinished basements, garages, outdoors, swimming pools, and any area near water or water sources. If you find a circuit not GFCI protected that is in an area around water or a water source, you should write it up as a safety hazard. GFCI protection can be provided by a GFCI outlet. This way you can install an outlet instead of changing the breaker at the panel. A GFCI outlet can protect up to 7 other outlets that are located downstream from the GFCI outlet. They do not protect the outlets upstream. In 1962, the electrical code was revised to require all branch wiring to include a grounding conductor or ground path. 2-prong outlets are not to be considered as a defect, but when they are found in older homes, the inspector should recommend upgrading the wiring to more modern grounded outlets. Most modern electronics, like computers and televisions, require a 3-prong grounded outlet. They will not be properly protected if plugged into a 2-prong outlet using an adapter. There are 2 reasons you should see ungrounded outlets. Either the outlet was wired improperly, or the wiring is done with 2 conductors. If all of the outlets in the home are ungrounded, it would indicate it's probably not a poor outlet installation, but a bigger problem of no 3 conductors in the house. Federal Pacific panels were shown not to meet the UL listing standards in the late 1980s. Since the UL label has been withdrawn, the panel should not be used as a residential panel. These breakers have a very high failure rate, and once they fail, the wiring will burn and thus cause a home fire. Smoke alarms have a lifespan of 8 to 10 years. Since we do not know when the alarm was installed, testing the unit is not the answer. You should advise all new buyers to replace all smoke alarms in the house with new units. Then those units should be replaced every 10 years. Carbon monoxide detectors have a lifespan of approximately 2 years. Inspectors should recommend to the client to install new carbon monoxide detectors and replace them every 2 years. Take a few minutes and review the next few slides. These are the inspection items for the electrical system.
This chapter dealt with, in my opinion, the most important and most safety-oriented section we have in the program. It was the electrical inspection. The most important thing to understand is this electrical system that is in the house affects every area of the house. It's out in the garage, it's out in the detached garage, it's in every bedroom, in the basements, no matter where you're at in the house is connected to the electrical system. So whatever's going on in the electrical system can affect any area of the house. I feel that it's mainly misunderstood the function of the main panel. The main panel is not a distribution box. The main panel isn't where all the wires are run together so the electrician can have an easy day of connecting it all to the breakers. That electrical panel's main function is to prevent fires. If you have too much current on a wire, the wire heats up. The hot wire starts a fire somewhere else in the house. The way you stop wires from heating up is by having operating, functioning, properly installed breakers. So I look at that main panel as a fire prevention device. That's all it is. I don't need a distribution box with all breakers in it. I can run all those wires together and those carry the current out throughout the house. I don't need a panel. The reason those breakers are there is to save lives. And that's what you need to remember when you're looking at the panel. And as a part of that, make sure that your wires are not undersized for the breaker. There's a lot of different things to look at, but the most important thing to look at is just make sure you don't have a 14 gauge wire on a 20 amp breaker. Because during Christmas, when all the lights are lit up and everything's going on in the house, now you have the potential for the house burning down. Just remember, that panel is the most important place in the house when it comes to safety, and that's your fire prevention center. Good luck on the quiz.